Yeah, so this is, if you remember, we had two charges on the x-axis. There was, like, let's say this was the x-axis, and we had a charge of 3q at minus d, 3q, and we had another charge, so this is minus d, right? And we had another charge of minus q at d. And so this here is also d. And we need to write the expression for the volume charge density for this system of charges. So the question is, what's rho of r, right? So this has, of course, to be in 3D. And remember, just to give you a hint, rho r is volume charge density. So this has to be, so the units here have to be in coulombs over meter cube. So you do have to consider a volume you do have to consider a volume integral, right? Such that when you integrate the rho, you would get the total charge enclosed in the volume, because you know that q in whatever volume you consider, it will be equal to the integral on that volume of rho d tau, right? So what would your rho r here be? Well, first of all, you need to take a sphere here, yeah? Your volume will be a sphere of radius. Well, this whole thing is 2d. So your radius would be d, right? And what is the total charge here, by the way? What is q? It's 3q minus q. It's 2q. So on that volume, you're supposed to get 2q over the volume of the sphere that you are considering, right? So this will be 2q. What's the volume of a sphere? 4/3 pi r cube, and r is d cube, right? But this is only on the surface. Because this is on the surface of the sphere, because there's nothing in between minus d and d. So you need to qualify this with a Dirac delta function, right? Where you could make this here an r, and you could say, okay, I want a Dirac delta function such that when I plug in d, this is r cubed, I would pick up the charge at d, but if I'm outside of d, the charge is 0, or no, the charge would still be the same, would be enclosed, right? Would still be 2q over 4 pi r cubed. But if I'm inside d, right, my volume extends out. Like, say, if let's say, for example, I take a sphere here. So my bounds of integration are less than d, then the answer will be 0. So what this is telling you is that if your bounds of integration are between minus d and d, you will pick up the charge that's enclosed. You will get 2q, and it's the integral will pick up the value of f, which is this, at r equals d. So you'll get 4/3 pi r cube, pi d cube, right? as long as as long as R as long as your sphere is including the point charges. So your bounds of integration are either equal to or less than d. So this is greater than d, for R greater than or equal to d. Yeah, or the bounds of integration including are d or greater. Yeah, so like when you integrate from somewhere greater than d or equal, greater than or equal to d, to b greater than or equal to d. This is minus d, but I'm using absolute value. You get my idea. You get what I'm trying to say here. As long as you go greater than d, right? If R equals d or greater, and it's going to be equal 0 if R is less than d, which makes sense because if your sphere is somewhere here, you're not going to pick any charge. You will get 0. So this Dirac delta function picks up the right values depending on where your sphere is. You see how to use this Dirac delta function? And this D. Yeah. Say that again.